Today in this session, we'll be talking about our experience using RocksDB to meet our performance goals. I'm from RCCM, so we'll start with some context of what we do at RCCM and why we needed something like RocksDB. Then we'll talk about some of the features of RocksDB itself. Then in the third section, I'll be talking about some of the challenges that we have faced while using RocksDB. And then lastly, I'll talk about some of the tips and tricks for using RocksDB in production. Let's get started. So what do we do at RCCM? RCCM is a product firm in Fintech space. We build products for large financial institutions to meet their post-trade requirements. Our engineers typically deal with scaling our systems to support the large volumes that is pretty much dependent on the market. We have to scale our systems to meet our customer requirements. So we offer these products as a SaaS model, and our newest offering is Aquata. So this is a domain-aware data platform. This is our recent offering. So basically, we are a fintech firm. We are building products in the post-trading space for large institutions. So what are some of the challenges that, as an engineer, someone faces at RCCM? So we are living in a very dynamic, volatile world where everything is decided by various geopolitical events that happen all over the world. So this is how the trading looked like over the course of 2023. So you see there is so much of volatility happening here throughout the year. So the data that comes into our products depends a lot on the market situation. And we have very strict SLOs defined on our products. So as a software engineer, we need to meet those SLOs. And if we don't meet any of those, there is so much of things at stake. So we will be losing our credibility, and our customers could potentially lose a lot of money. And there is also a risk of not meeting the regulatory requirements. So these are some of the unique challenges our engineers face. So first thing, we need to meet the performance. If we don't cater to the agreed upon SLA, there could be reputation at stake, and there could be potential dollar value loss for the users as well, for our customers. Then we have to be very accurate. The data integrity is crucial. So given that we are in a financial world, even if we are off by few dollars, we will lose the trust on our customers and will not be able to sell our products. And data security is again crucial. So as an engineer, irrespective of the data that comes into the platform, we should still build our system that is scalable enough to meet these data volumes and meet these performance goals. And we should be able to still operate in a BAU state. So that's the expectation of a software engineer. So we deal with these large volumes of data. We'll worry about how to store them efficiently so that we can retrieve them in a fast and efficient way. We'll worry about how to scale our compute engine so that we can process these large workloads without delaying any of the SLA that we agreed upon. I've been part of this team where we have to process millions of events in a near real-time fashion. So these events come to us in a bursty fashion. So typically towards the end of the day, end of the trading day, as the trading closes in the market, so we'll be getting these events in a very bursty fashion to our product. And on a certain day, we could be getting million events. On another day, we could be getting 100K events. We should still process them with the same agreed upon SLO, which is roughly around 5 minutes to 10 minutes. To meet those SLOs, we do a math, right? And one other unique aspect of these events are they're all sequential, okay? So to give you an example, so a hedge fund doing a lot of transactions on a single security or a single stock. For example, I'm buying 100 shares of IBM. Then I'm selling 20 of them 2 minutes later, then I'm buying it again, I'm selling. So if I keep continuing transactions like that, so I don't have luxury of processing them in a parallel fashion. So I'll have to process them in a sequential fashion. So that's when they'll be accurate. So we have to process these events sequentially, and the calculations are also very complex within these engines. So we have to process them sequentially, and at the same time, we have to meet that SLO. If you look at the per event processing latency, it comes to somewhere less than a millisecond. So we are talking about sub-millisecond latency, That's what we wanted to achieve in our products. So if you look at sub-millisecond latency, and if you're processing something, you want to write something into the database, if you look at any off-the-shelf database products, they'll invariably have some bit of a network lag. So you'll have at least a few millisecond network lag. So we don't have so we cannot definitely use a network database for this use case. So that's when we wanted to, we started exploring some of the embedded databases or databases that are co-located. So today we talk about a lot of co-located compute, where we are moving the compute closer to your data. So we wanted something like that. We wanted something which sits close to our data so that there is no network transfer and all that. And our data and the compute stay closer to each other, and we process them efficiently and meet our performance goals. Yeah, so with those requirements, so as I said, there were two key requirements. The first thing, we need to process them with the sub-millisecond latency, and we wanted the data to be co-located with the compute. So with those two requirements in mind, we were looking at all the options. And so this got reminded us of this meme which came 30 years back, where this pointed hairy boss wanted to build a SQL database when SQL databases were popular. He was jokingly saying that he wanted to build a database, and so they were having fun around building a database. But we were exactly in that stage 30 years later, where for our workloads, so most of the other databases were not meeting our needs, and we were in a situation where we wanted to build a database on our own, okay? And so we did a little bit of research. We studied how various databases are built, what goes into building a full stack database. So we dissected a lot of the databases that are available. And if you look at it, if you look at the architecture of some of the open source relational databases or NoSQL database or any database for that matter, invariably the lowermost level will be something called as a storage layer, which is typically a key value store. That's where the underlying data gets stored. So any database, you dissect MySQL, or there are NoSQL databases like Cockroach or whatever it is, the underlying layer is a storage layer, which is typically key value pair. And we then decided that we wanted to try out something on the one of those key value stores, one of those embedded key value stores. We did a lot of research, and we ended up choosing RocksDB. So why did we choose RocksDB? Because it was fast, it is scalable, and there were so many players behind it. So today, if you look at the usage of RocksDB, it's used by almost all the popular products. Like Microsoft uses it in their Bing platform, LinkedIn uses it, so Facebook heavily uses it. So Facebook backs the so they are the ones who are maintaining RocksDB currently, and they have a MySQL implementation which is backed by Rocks, and they use Rocks in multiple other distributed systems of theirs. So it was very well adapted, and the community also was very vibrant. It's still open source. There are so many people actively contributing to it. So the community was very vibrant. So that's why we decided to go with RocksDB. And we did some POCs to understand the performance of it. So it was meeting our performance. So we decided to go with RocksDB. So what is RocksDB? So RocksDB is a high performance key value store. It was originally written in C++, and it's currently managed by Facebook database engineering team. And so we use it in Java via the JNI route. We use a JNI bridge. That's how we use it. And so these are some of the basic operations. It's a very simple database. If you look at it, it offers only 5-6 databases, 5-6 operations. It starts with opening a database, to which essentially you need to give a file path, and it'll go and write the data to that. And then there's a close operation, and there is a get operation, which is for reading the data. Then there's a put operation for writing data into that. And then there is a delete. These are the basic single value operations. And then there is also an iterator. So if you want, so typically so this is a key value pair, right? So in RocksDB, your key can be a byte, any arbitrary set of bytes, and your value can also be any arbitrary byte array that you want to store. So if you are using any keys, so the only constraint is you have to have a comparator, and internally Rocks stores your data in that sorted order of keys. So that's how data is internally stored. So Rocks is actually it's built on top of LSM tree, That's the data structure ROCks use. So if you have heard about log structured merge tree, ROCks is built on top of it. That's a data structure optimized for writes. So it uses append data structure, append model, where your writes are getting appended rather than it goes and modifies the existing value. So yeah, I mean, it's interesting. If you want to read more about it, you can go to the RocksDB website and read more about it. They have very good documentation where they talk about the underlying implementation of it. So the next operation, coming back to this, the next operation is iterators. So as I said, like key is arbitrary set of bytes and value is bytes. So now if you want to scan through them, if you want to iterate through them, there is an iterator wherein you can set a lower bound and an upper bound. Then it will iterate over that and you can read each of those values. So these are some of the basic operations which are fast enough in RocksDB. And then there are these basic internal constructs that one should be aware of. So Rocks leverages multiple layers of storage. It starts with memtable. So when you write or when you read something, first it goes into in-memory data structures called memtable. This is again like a complex, you can think of it like a hash map, but it's much more than that. It has some keys and ordering, and it has indexes and all that. So that's the first layer where all your reads and writes go there. And then after that, it gets flushed into SST. But before it gets into the file system, there are two more layers. There's a block cache where you can choose to use. There is also a OS page cache where the data goes through. So there are these 3 or 4 layers where your data resides before it actually goes and sits in the underlying file system. And it also has a log files. Primarily wall write-ahead log, as we call it. This is used for managing the data in memory. So whenever you're having lots of transaction and your application crashes somewhere in between, if you want to recover from that stage, wall is primarily used for that. It's used to recover from whatever state that you're in. So wall is primarily meant for that. And it has a bunch of other features. I'll touch upon some of those critical ones. There's a notion of column family, where this is like a logical partitioning of your data. So this is like, so instead of storing everything in a same key val space, you can break them down into multiple column families. So that's the column families capabilities. And so in Rocks, as I said, it's an LSM data structure. So it is immutable by default. So what that means is, so let's say I'm putting a key K and value as V. So it will go and insert it first. Let's say it's flushed into SST file. Then later at a certain point, I am trying to update that value from V to V1. So it will not go and mutate that existing value. Instead, it adds a new byte. Okay, it adds a new value to the top of the tree. And your iterator is built in a certain way that you will never reach the older versions are not reachable. You will not be able to read that old value unless you explicitly restore those SST files. Those files are still present in disk. All the versions are there in disk, but you will never be able to use them unless you go and read them. Okay, so that's the immutability aspect of it. It has its own pros and cons. We'll talk about one of the issues that we faced with this particular aspect of Rocks and how we mitigated that. I'll defer that conversation till then. Then there is also a concept of snapshots and iterators. So when you use iterators, essentially it will lock all the state of those files and it will give you the, so basically when you're iterating over a key space, if the underlying data changes, you can decide whether you want to take those changes or you don't want those changes. Typically it creates a snapshot wherein not a snapshot is a different concept, but pinning is the right word. It pins all the files that are needed for that iterator. And when you are performing that operation, so those files won't be discarded, they won't be compacted, or nothing will happen on those files. Then it also has a concept of transactions, wherein you can begin transaction if you want to do a bulk operation. If you have a bunch of keys that you want to update together, you can use this transactions capability. Then there is a block cache, which is like another, you can define whether you want LRU or other strategies. Then compaction, I'll come to compaction also, why we needed, why it's critical, in another issue that we have faced. I'll move on to the next one. Okay, these were some of the salient features of RocksDB. There are many more to it, but these are the things that made it lucrative for us to use. It was super performant, it had all the basic functions, just easy to use, and we were able to get started pretty quickly. Now, let's look at some of the challenges that we faced as we started using it in our production workloads. And by the way, we have been using it in production for like at least 3 years now. Okay, let's look at some of the challenges that we have faced. The very first thing is the index management itself. So if you, as I mentioned, it's a single key value store. So one of the thing is you have to define your key, you have to design your key in a way that it's more suitable for your primary access pattern. So if you have so let's say I wanted to maintain the list of all stock prices, I wanted to read it based on a certain, so I want to find out how Google has changed over the years. So I might define my key in a certain order, certain fashion. But now later at a different point, I have a different access pattern. I want to access the same data in a different way. So in a typical database, we will have different indexes created on it, and we will be using indexes to fast track the access. So, but here we don't have an index natively available. So we will have to build something like an index ourselves. So we can leverage the other additional column families for that purpose. So that's what we do. So this is a quick example where, so I was telling you, so our keys are typically complex. So this is how we have modeled our keys. So let's say this is an example of how we are storing stock prices, okay? So the first one is the event ID, which says what is the stock. So here Google or Qualcomm, Apple. The second one is a valid time, which talks about what was the period for which this price is applicable. So it says that the first one represents 0424, yesterday's price, then current day's price, then Qualcomm yesterday's price, current day price. Then the last value, last part of that key is the knowledge time, which is the time at which we recorded. In a financial institution, these are common things like valid time and knowledge time is something that we obviously use in all the data structures. So, so this is how we have modeled our key, and the value is the actual value itself. Now, in this kind of a column family, now if I want to, so there could be two kind of query patterns. One is I might want to query for the historical price of Google. So this is my primary use case, let's say. So I can then set my lower bound of the iterator to Google and the upper bound to be Google, and I'll add a additional special character to mark it as a terminator. So then it will scan only in that key space, and I'll be able to quickly read that data. Now, let's say there is after a certain point in time, there's a new use case comes in where I wanted to access the same data by date. I want to look at prices of all the stocks for today, okay? If let's say that's a different use case. So what I can do is, so if I have to query in that same key val pair, I'll end up doing a full scan. I'll have to read through the entire key span, and then I'll have to only access the ones which have valid time in that range. So the way we solve it is by building a secondary index. So we'll have a secondary index in a different column, key val pair. The key for that will be the valid time itself. I'll use a suffix as sequence number, and then the business key will be the value there. So this is the index that we have actually built to make this scan faster. So now with this new index in place, our access pattern will change. Like you will first scan that index, and which will be, again, you will set a lower bound as 2024 04 25, and you will set it to tomorrow. So it will scan all the keys in that space, and you will read the values. Those values themselves are keys for the original data, your business key itself. So that you can do either individual lookups if the number of keys are smaller. There is also a multi-get operation wherein you can pass a set of keys and you can get it, or you can do a range operation. Yeah, these are some of the things that you need to deal with. So basically, based on your access pattern, you'll have to tweak your indexes, and you'll have to be on top of it based on your access pattern. Without that, the performance will not be good. And we also had to do a special handling for numbers. We have come up with an encoding scheme for handling numbers, because when we typically use lexical ordering for sorting, and if we have numbers, so 1, 2, and 11, so 11 gets sorted before 2. That's how typically in a string order happens. So to handle that, we do some encoding, and then so that it's still sorted using strings, but then they'll still be sorted based on their numeric value. So this was the first problem. Then the second one was something called as a tombstone bloat. Tombstone, so this goes back to the immutability. So we spoke about how rocks essentially manages the writes. So whenever you are putting in a new key, and if it's an amend or a deletion, so if it's an amend, it will essentially leave the old value as such, it will create a new value, and your scans and other things will go into that new value. If you have a deletion, similarly, it won't touch the existing value. Instead, it will create a new entry and it will place a marker. It will place a deletion marker there or a tombstone marker, and but the record will still be there. The older value will still be there. On the new, it will be for the same key. It will add a marker indicating that the data, the key is deleted. So when you have a usage pattern where you are doing a lot of deletes in your data, then will lead to a problem called tombstone blot, where your SSD files will be left with too many blots like that, which will slow down your scans. It will slow down your overall performance. So to solve that, there are two solutions here. I'll come to the first one later. But the first option you have is something called delete range. Instead of deleting each key at a time, if you know a range of keys that you're going to delete, always prefer using delete range. So delete range, the advantage is instead of keeping a marker for each of those keys, it will place a marker for the entire range, thereby reducing the number of tombstones markers. That's the first way to solve this. The second one, which is obviously recommended at some point, you will have to use it, is compaction. So compaction is a native RocksDB process, it's a RocksDB feature, which goes through all your SSD files and it will shake up the LSM tree. When you have a LSM tree, it will look at merging the level. So LSM has multiple levels. L0 is your latest data, then L1, L2, L3, like a tree-like structure. And when you do the compaction operation, again, there are different styles there. We use something called leveled compaction. When you do the compaction, it will try and shake the tree, and it will try to remove all the keys which have been deleted. It will merge level 1 to level 2, level 2 to level 3. It will make sure that these kind of values that we had, which had multiple versions, all those are shaken up, and your overall size will reduce, and they will all be compacted. So reads and other things will get performant. But this is a very heavy operation. That's the thing that you need to keep in mind. So it works very well, but you cannot do it more frequently. And in fact, Rocks also tries to do this compaction or a flush after every flush. Whenever you're writing something to the actual disk, it tries to do a compaction. But it does it only for L0 to L1 level, not for all levels of SSD or the tree. So you need to be very cautious about when you are scheduling this. So in our case, we do it on a daily maintenance window whenever the maintenance happens. So in that window, we try to schedule this. That's how we handle this. Then lastly, this is one of the another problem. If you are running Rocks instance in a Kubernetes container, and if your process is a very long running process, so how much ever your off-heap memory keeps growing. I believe some of you guys would be aware of the off-heap memory. So off-heap memory keeps growing when you run it on a container over time. And like initially we were suspecting this to be an application problem. We were inspecting, we were taking memory dumps to see whether we were leaking anything in the application layer or in the places where we have rocks objects or iterators. So you need to close all those objects promptly. So we were just doing a quick review of all that. So but even after that, we noticed that memory kept on growing. So that's when we realized that the underlying memory allocator that we use, so as I said, like we use it via JNI, and the underlying, so the memory allocator that we use was Memalloc. That's the one which allocates the memory needed for various objects of RocksDB, like the mem table, indexes, filters, and all that. So, and apparently Memalloc has a serious bug when it comes to memory allocation. So it was not releasing the memory. So there were multiple things that we did when we were in this stage. So the RocksDB itself has a tool called Advisor. So advisor accept a log and a statistics file from rocks, and it provides you suggestions or parameters that you have to tweak. So we tried that. So it helped us to stabilize the memory growth, but then it also resulted in a degraded performance. Yeah. So that didn't work out. So we didn't wanted, so whatever suggestions that the tool gave us was not useful in our use case. So we had to try out different memory allocators. So this is a common known problem. If you search for ROCks memory management or memory allocator, so there are many other people who have faced this problem. So we also tried multiple other memory allocators. We tried something called tcmalloc. We tried gemalloc. So eventually we went with gemalloc. That's the one which gave us the best performance. Yeah, I think these are some of the problems that we faced because we used RocksDB, and these are not very common problems that you face in a typical application. And given that we have chosen RocksDB, these are problems which are very unique to us. And in fact, it might be unique to some of the other LSM-based databases as well. So, so let's look at using RocksDB in production. So whether RocksDB is suitable for everyone, I don't think so. So unless you have a real use case where you want to be really fast and you have a workloads which you need to cater to, you don't want to use it. And even if you are using it, you might probably want to use it with the basic parameters. So Rocks comes with a basic set of default performance parameters. You might want to continue with that because when you're trying to tweak the performance, it might become a rabbit hole and you might not get the necessary performance. So don't tweak anything prematurely. Look at the data, use the performance, use the parameters as is as much as possible. There is also a Bloom filter, which is a probabilistic data structure, which is used for doing faster lookups. It helps you to decide whether a key exists in your tree or not. So if you haven't come across Bloom filters, go read about it. It's an interesting data structure. So when you're talking about going live, you also need to worry about so many other things, like how do you back up and restore your database. So you need to have so if you look at any other database, you have those solutions, but Rocks also, we need to have something. So Rocks natively provides backup and restore functions, but then you have to take care of move that data into like a persistent store like a S3 or some other place. So you need to build some solutions around that. We spoke about compaction, like you have to have periodical compaction, and it's also recommended to do some archivals. If your data is old for a certain period, you might want to take them out and move them into a different store. Lastly, it has a bunch of admin tools, like there's something called LDB. So this is one of the major problematic area that we have seen. When you have large volumes of data and you have to debug a production issue, it's very hard to know what is there in the DB. So you need to have very good tools. So my recommendation is whenever you're wanting to use RocksDB, focus on building a tooling which will help you to introspect the rocks so that you have a better visibility into what is there inside. Then the last thing is logging and monitoring. Rocks provide a good amount of logs and statistics on IO and the disk usage and all that. So we had built a solution to extract these logs and push it into Prometheus. You might want to do it for whatever the monitoring tool that you're using. So few of the learnings. So Rocks is a very super fast database, but it's not for everyone's use case. You might want to consider, do you really want to use it? You need to take a call on that. If you want to be a good distributed system engineer, don't just use these distributed systems. You might want to build one. So you can take Rocks as the base and probably try building some distributed databases on top of it. So you'll be able to, that'll be a cool fun project where you can learn a lot. Yeah, I think that's it from our side.